Time travel has captured humanity's imagination for as long as we've been aware of time itself. We measure time constantly, clocks tick, seasons change, the earth spins on its axis, and the sun rises and sets. But all these things are merely markers. They do not define what time truly is. Time is abstract. We cannot see it, touch it, or hold it. We cannot slow it down, speed it up, or reverse its flow. Yet time governs everything, every heartbeat, every thought, the birth and death of stars, the rise and fall of civilizations. For thousands of years, philosophers have tried to understand time. The ancient Greeks described it as a river, always flowing forward, never backward. The philosopher Heraclitus famously said, "You cannot step into the same river twice." Centuries later, Isaac Newton believed time was absolutely universal clock, ticking the same for everyone, everywhere, unchanging and independent of the universe. But in the early 20th century, Albert Einstein shattered that belief. Einstein's theory of relativity revealed something extraordinary. Time and space are not separate entities. They are woven together into a single fabric, space-time, and that fabric can be stretched, bent, and twisted by motion and gravity. This means something astonishing: time is not absolute. If you travel close to the speed of light, time slows down for you relative to those you leave behind. If you stand near a massive source of gravity, a black hole, for instance, time also slows down for you compared to someone farther away. This is not just theory, it has been measured. Astronauts on the International Space Station age slightly more slowly than people on Earth. After 6 months in orbit, they are a fraction of a second younger than if they had stayed on the ground. But fractions of a second are not what we dream about. We dream of something more, of stepping into a machine and emerging centuries ahead or centuries back. Is that possible? The surprising answer is yes, at least in one direction. Einstein's relativity guarantees that we already know how to travel into the future. The phenomenon is called time dilation. Imagine boarding a spacecraft capable of traveling at 99.9% of the speed of light. On board? Only 5 years pass. But when you return to Earth, decades or even centuries could have gone by. This is not science fiction. It is an unnatural consequence of how the universe works. The faster you move through space, the slower you move through time relative to everyone else. We have tested this in the real world. In the 1970 seconds, physicists Joseph Haffel and Richard Keating flew atomic clocks on commercial airliners, then compared them to identical clocks that stayed on the ground. The airborne clocks ticked more slowly. The difference was tiny nanoseconds, but it was exactly what Einstein predicted. Nature shows us the same phenomenon with moons. Unstable subatomic particles created when cosmic rays strike Earth's atmosphere. Moons decay in microseconds. Most should vanish before they ever reach the ground. But they don't, because time dilation slows their internal clocks, allowing many to survive long enough to be detected. In particle accelerators, when moons are pushed close to the speed of light, their lifespans stretch dramatically. Without time dilation, they would decay too quickly to study. This is time travel into the future. And it is real. Astronauts experience it too. On the International Space Station, they orbit Earth at more than 27,000 kilometers per hour and experience slightly weaker gravity. Their time runs a bit slower than ours. After 6 months in orbit, they are microseconds younger than if they had remained on Earth. At everyday speeds, the effect is negligible, but at relativistic speeds, near the speed of light, the difference becomes dramatic. However, there's a problem. Time travel into the future is a one-way trip. Once you leap ahead, there is no way to come back, and the energy required is staggering. As you approach the speed of light, your relativistic mass increases, and it takes exponentially more energy to accelerate. At 99.9% of the speed of light, even a small spacecraft would require more energy than humanity could produce in centuries. What about using gravity instead of speed? The stronger the gravitational field, the slower time moves. If you could orbit just outside a black hole's event horizon, time for you would pass much more slowly than for someone far away. Hours near the black hole could correspond to years or centuries elsewhere. This was shown dramatically in the movie Interstellar, where 1 hour on a planet near a black hole equaled 7 years on Earth. That concept was based on real physics. But black holes are dangerous, stray too close, and tidal forces would rip you apart. And even if you survived, you could never reverse the effect. Once you leap forward, you are stuck. There is another challenge: navigation. If you jump centuries ahead, where will Earth be? Our planet orbits the Sun, which orbits the galaxy, which itself moves through the universe. By the time you emerge, Earth could be light minus years from where you expected. To time travel safely, you must control not just time but also space. So forward time travel is possible in principle but impractical in practice. And that leaves us with the question we truly crave to answer: can we travel backward? Backward time travel, unlike forward travel, introduces paradoxes. Backward time travel has always been the most tantalizing and the most troubling concept in physics. Forward travel is easy to explain. Relativity guarantees that if you move quickly enough or spend time near an intense gravitational field, you'll leap ahead. But the idea of going backward, returning to yesterday or to an era long before you were born, introduces problems so severe that some scientists believe it might be fundamentally impossible. The core issue is causality, the chain of cause and effect that governs reality. If you travel backward in time, you can change the past. But if you change the past, you risk undoing the very conditions that allowed you to travel back in the first place. This is the famous grandfather paradox. Imagine you go back in time and prevent your grandparents from meeting. If you succeed, you erase your own existence. But if you were never born, how could you have traveled back to stop them? To resolve this contradiction, some physicists propose the Novikov self minus consistency principle. This principle suggests that the universe forbids paradoxes. Any actions you take in the past must be consistent with the timeline that already exists. In other words, you could visit the past, but you could never change it. Imagine you travel back with the intention of preventing a historical disaster. Every attempt you make fails not because of bad luck, but because success would violate the timeline. Worse, your actions might turn out to be the cause of the very disaster you hope to stop. This approach preserves causality, but it raises troubling questions about free will. If the past cannot be changed, is the future also fixed? Are we simply acting out a script written by the universe? Other physicists turn to quantum mechanics for answers. The many minus worlds interpretations suggests that every possible outcome of an event exists in its own branch of reality. In this view, traveling into the past would not rewrite your original timeline. Instead, it would create a new, parallel universe where your actions take effect. For example, if you prevented your grandparents from meeting, your original timeline where you were born would remain untouched, but you would create a new universe where you never existed. This elegantly avoids paradoxes, but it comes with a price. You could never return to the reality you live. Once you branched off, your original world would be forever beyond your reach. Even if paradoxes can be avoided, we still face the enormous challenge of how to travel backward in time. One of the most fascinating ideas involves wormholes, hypothetical tunnels through space-time that connect distant points. Imagine space-time as a sheet of paper, with two dots at opposite ends. If you fold the paper so the dots touch, you create a shortcut. A wormhole would be that shortcut. In theory, wormholes could connect not only distant locations, but also different moments in time. If one mouth of the wormhole experienced time more slowly than the other because it was near a black hole, or accelerated close to the speed of light, stepping through could take you to the past relative to where you started. But there's a major problem: wormholes, if they exist at all, are unstable. They would collapse almost instantly, crushing anything that tried to pass through. To hold a wormhole open, you would need exotic matter, with negative energy density. Quantum physics allows for negative energy in tiny amounts. We see hints of it in the Casimir effect, where quantum fluctuations in a vacuum create a small negative energy field between two closely spaced plates. But creating enough negative energy to stabilize a wormhole large enough for a human or a spaceship to pass through is far beyond our current capabilities. Even if we could build and stabilize a wormhole, using it as a time machine would be risky. What happens if you emerge before you enter? Could you meet yourself? Could you create paradoxes that erase the future you came from? Stephen Hawking believed the laws of physics might prevent this altogether. He proposed the chronology protection conjecture, which suggests that the universe would destroy any time machine before it could create paradoxes. Wormholes remain one of the most fascinating possibilities for backward time travel, but they are only the beginning of the questions we must ask about the nature of time itself. To explore further, we must venture into the smallest scales of reality, the quantum world, where time may not behave the way we think. Backward time travel has always fascinated physicists, but to understand whether it's even possible, we need to explore the tools the universe might give us. And one of the most compelling ideas comes from wormholes and other exotic structures predicted by Einstein's theory of general relativity. Einstein's equations tell us that space-time can bend in curve. If it can be bent enough, perhaps it can fold back on itself, creating shortcuts we call wormholes. Imagine space-time as a sheet of paper. Draw two points at opposite ends. Normally, the distance between them is the straight line along the sheet, but if you fold the paper so the 2 points touch, you create a shortcut. A wormhole is that shortcut. In theory, wormholes could connect not only to distant locations in space but also different points in time. If you could take one mouth of a wormhole and move it close to the speed of light, time dilation would slow its clock relative to the stationary mouth. Then, when you bring it back, the two mouths would be at different points in time. Step through the younger mouth, and you would emerge from the older one, effectively traveling into the past. This isn't just science fiction. The math behind it is solid. But wormholes, if they exist, would be incredibly unstable. They would collapse in a fraction of a second, long before anyone could pass through. To hold a wormhole open, we would need something extraordinary: negative energy. Negative energy is not like ordinary energy. It would repel gravity instead of attracting it, counteracting the wormhole's tendency to collapse. Quantum physics suggests that negative energy can exist in tiny amounts. We see hints of it in the Casimir effect, where quantum fluctuations in a vacuum create a negative energy field between two closely spaced plates, but the amount required to stabilize a wormhole big enough for a human would be astronomical. We have no idea how to create or control such energy. Even if we could, we would still face serious risks. What happens if a wormhole mouth is moved incorrectly? Could it destabilize and create a black hole? Could it swallow entire planets? And even if we managed to enter one, could we be sure where or when we would emerge? Wormholes aren't the only possible path to backward time travel. Some physicists have proposed tubular cylinders, infinitely long, rotating cylinders of ultra-dense matter. If you traveled around one fast enough, you could, in theory, loop back into your own past. But building a cylinder of infinite length is obviously impossible, and even finite versions would require matter so dense it might only exist inside neutron stars. Another concept is cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe. If two cosmic strings pass near each other at high speed, the extreme warping of space-time might allow closed time-like curves, paths that loop back in time. But cosmic strings remain purely hypothetical. We have no evidence they exist. Even if these methods could work, there's another problem: the universe itself may resist backward time travel. Stephen Hawking proposed the chronology protection conjecture, which suggests that any attempt to create a time machine would fail. Quantum effects might destroy the wormhole, tubular cylinder, or cosmic string the moment it became capable of allowing backward time travel. This would protect causality and prevent paradoxes like the grandfather paradox from occurring. But we don't know if Hawking was right. Forward time travel uses natural effects, motion and gravity. We've measured time dilation. We know it works. Backward time travel, on the other hand, requires engineering space-time in ways that may be impossible. It demands negative energy, exotic matter, or cosmic minus-scale structures we don't even know exist. And even if we could overcome those challenges, the paradoxes would remain. If backward time travel is possible, it could rewrite history. We could visit the dinosaurs, witness the birth of stars, or stop catastrophic wars. But we could also create paradoxes that destabilize reality itself. This is why so many scientists approach the idea with caution. To understand time travel fully, we must go deeper beyond relativity, beyond wormholes, into the world of quantum mechanics, because at the smallest scales of reality, time behaves in ways that challenge everything we think we know. The quantum world is unlike anything we experience in daily life. It is strange, unpredictable, and at times, it seems to ignore the common minor sense rules we rely on. And when it comes to time, quantum mechanics may hold clues that could change everything we think we know about the past, the present, and the future. One of the most famous experiments in quantum physics is the double minus slit experiment. The setup is simple. You fire a beam of particles, photons or electrons, at a barrier with two slits, and then record where the particles land on a screen behind it. When you open one slit, the particles pass through and create a single band on the screen. That's what we expect. But when you open both slits, the particles form an interference pattern, a series of light and dark fringes, like overlapping ripples in water. It's as if each particle is somehow passing through both slits at once, behaving like a wave. Then, something even stranger happens. If you place a detector at the slits to see which path the particles take, the interference pattern vanishes. The particles behave like solid objects again, choosing one slit or the other. The act of observation changes the outcome. This result challenges our deepest assumptions about reality. Does it mean that the future, the moment you measure the particle, can affect the past when it traveled through the slits? To test that idea, physicists developed the delayed minus choice quantum eraser experiment. In this version, you decide whether to measure the particle's path after it has already passed through the slits. And yet, the interference pattern still depends on that delayed choice. It's as if the particle's past behavior, wave or particle, is determined after the fact. Most physicists say this does not mean the future is literally rewriting the past, but it does suggest something important. The boundary between past and future is not as solid as we once believed. Quantum entanglement adds another layer of mystery. When two particles are entangled, their states become linked, no matter how far apart they are. Measuring one instantly determines the state of the other. Albert Einstein called it spooky action at a distance, because it seems to violate the universal speed limit set by the speed of light. In 2017, scientists used entangled photons to connect to ground stations in China more than 1,200 kilometers apart, through a satellite called McIOS. The experiment confirmed that entanglement works even across vast distances. Does this allow information to travel faster than light or backward in time? Most physicists would say no. But entanglement suggests that reality is more deeply connected than we understand. Some researchers even think entanglement and wormholes might be connected. Physicists Juan Maldaceno and Leonard Susskind proposed the REPR conjecture, which suggests that every pair of entangled particles is connected by a tiny quantum wormhole. We cannot travel through these wormholes, but they link particles instantly. If true, wormholes may be everywhere, happening constantly at the quantum level. What does this mean for time travel? It might mean that time is not as linear or rigid as we think. In everyday life, we think of time as a one-way street. The past is fixed, the present is now, the future is unwritten. But in the quantum world, particles can exist in multiple states at once, only choosing an outcome when observed. The delayed minus choice quantum eraser experiment shows that what we do now can, in some sense, determine what has already happened. Could we use this to travel through time? That's the challenge. Quantum effects are fragile. They happen at the smallest scales, and they vanish when we try to scale them up. We can manipulate single particles, but not human minus-sized travelers. Even if we could, paradoxes would remain. Could we prevent catastrophic butterfly effects? Could we ensure the time machine would not tear the universe apart? For now, quantum mechanics raises more questions than answers. But it does teach us one thing: time is not simple. It depends on motion, on gravity, and perhaps even on whether it is being observed. And if time is flexible, maybe it can be controlled. That's why physicists are working to merge general relativity and quantum mechanics into one theory: quantum gravity. If we can understand how space-time works at the smallest scales, we might find new ways to manipulate. But we are not there yet. The quantum world reminds us that reality is far stranger than it seems. We like to think of time as a river, flowing steadily from past to future. But at the quantum level, that river twists, loops, and sometimes seems to flow in more than one direction at once. And maybe, hidden in that complexity, lies the key to time travel. If quantum physics has taught us anything, it's that time is more flexible and mysterious than we ever imagined. But understanding time is not enough. To travel through it, we must learn to control it. At present, all of our time manipulation methods are passive. We orbit Earth in satellites and experience tiny differences in time. We observe particles in accelerators that live longer at high speeds. We understand how gravity and velocity stretch time. But all of these effects are minuscule, and may only allow forward travel by fractions of a second. To build a time machine, we would need to manipulate space-time itself on an unprecedented scale. One approach is to harness massive amounts of energy to warp space-time. We know that mass and energy curve space-time. That's why planets orbit stars and why black holes trap even light. If we could control that curvature, we could create paths through time. This is where the idea of warp bubbles comes in. In 1994, physicist Miguel Alcubierre proposed a theoretical faster minus than minus light drive. The Alcubierre drive would compress space-time in front of a spacecraft and expand it behind, allowing the ship to surf on a bubble of warp space. Because the ship never moves faster than light relative to the space around it, the drive would not violate relativity. But Alcubierre's equations also suggest something else under certain conditions. A warp bubble could allow travel backward in time. The catch? The energy required would be astronomical. To create a bubble large enough to carry a human, we might need more energy than is contained in entire stars. And even if we could generate that energy, the bubble would require negative energy to stabilize, just like a wormhole. Negative energy is not something we can produce in meaningful quantities. Another idea involves black holes. We know that the immense gravity of a black hole slows time dramatically. If we could position ourselves just outside the event horizon, we could experience hours while centuries pass elsewhere. But getting close enough without being torn apart is nearly impossible. And again, this only allows forward travel. Cosmic strings and typeless cylinders are also possibilities, but each requires materials and engineering we cannot yet achieve. We might need infinitely long cylinders or one-dimensional defects in space-time left over from the early universe. These ideas are fascinating, but purely theoretical. And even if we could build a time machine, the dangers would be immense. We would need stability. Any small disturbance could cause catastrophic collapse. And then there are the paradoxes. Backward time travel could unravel causality. Would the universe rewrite itself? Would it split into parallel realities? Or would it collapse entirely? Some physicists, like Stephen Hawking, believe the laws of physics protect the timeline. His chronology protection conjecture suggests that the universe prevents paradoxes by destroying time machines before they can function. But this is just a hypothesis. Until we know for sure, we cannot rule out the risks. And even if paradoxes were not a problem, The ethical questions are enormous. Who would control time travel? Would governments and corporations decide when and where to go? Would we change history to fix mistakes? And who would decide what qualifies as a mistake? The butterfly effect looms over everything. One small change in the past could ripple forward in unpredictable ways. A single action could save millions or doom them. For now, the best we can do is continue learning. We must deepen our understanding of space-time, gravity, and quantum mechanics. We must work to unify general relativity with quantum mechanics into a true theory of quantum gravity. That unified theory could reveal the true nature of time and how to control it. But until then, time travel remains just out of reach. We can move forward, yes, but the past remains hidden behind a wall we do not yet know how to climb. If we want to unlock the secrets of time travel, we need to push the boundaries of physics further than ever before. One possible path lies in understanding how the universe itself began. But Big Bang theory tells us that the universe started as a single, incredibly hot and dense point, nearly 13.8 billion years ago. In the first fraction of a second, it expanded faster than the speed of light in a process called cosmic inflation. That brief moment shaped everything: the galaxies, stars, planets, and life that followed. But inflation may also hold clues to the nature of time. During inflation, space-time itself expanded at an unimaginable rate. If we could recreate even a fraction of that effect, we might be able to manipulate time. But how could we possibly trigger something as powerful as the Big Bang? The answer is we can't. At least, not yet. Black holes may offer hints. A black hole is essentially a collapsed star, so dense that not even light can escape. Some theories suggest that the singularity at its core may contain conditions similar to the Big Bang. If we could understand what happens inside a singularity, we might unlock new ways to manipulate spacetime. Unfortunately, we can't study black holes up close. Anything that crosses the event horizon is lost forever. Even our most advanced telescopes can only observe them indirectly, by watching how they affect the space around them. But new tools are helping us learn more. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. It showed us the silhouette of the event horizon for the first time. New observations of Sagittarius A, the supermassive black hole at the center of our galaxy, bring us closer to understanding how spacetime behaves under extreme conditions. Could black holes be natural time machines? In theory, yes. If you could orbit just outside the event horizon, time would pass much more slowly for you than for the rest of the universe. But, again, that only allows forward travel. To go backward, you would need something even more extreme: connect one black hole to another with a wormhole. Wormholes might already exist inside black holes, but we would need to find a way to enter one without being destroyed and emerge somewhere safe on the other side. Even then, the wormhole would have to remain stable long enough for travel. Another path is studying the early universe. The laws of physics we observe today may have been very different in those first moments after the Big Bang. If we can understand those conditions, we might discover that time itself behaves differently at extreme energies. Some physicists believe that the universe might have multiple dimensions of time, not just one. This is a radical concept, but it is naturally in some quantum gravity and string theory models. If true, we may only be perceiving one slice of time while other directions exist beyond our awareness. Accessing those dimensions could open entirely new forms of time travel. String theory suggests the fundamental building blocks of the universe are tiny vibrating strings of energy. These strings may vibrate in up to 11 dimensions. In such a framework, time might not be a simple linear flow. It could be a complex landscape, with paths leading not just forward, but sideways and backward. But string theory remains unproven, and even if it's correct, we don't yet know how to access extra dimensions. They may be curled up at scales so small that no experiment could ever reach them. There is also the possibility of a multiverse. If other universes exist, could we travel from one to another? In theory, this could bypass the paradoxes of backward time travel. If you changed something in another universe, it wouldn't affect your original timeline. But we have no evidence the multiverse exists, and traveling between universes might require energies and technologies beyond imagination. All of this highlights a humbling truth: we have only just begun to scratch the surface. We need another revolution in physics, something as profound as Einstein's relativity or the discovery of quantum mechanics. Only then might time travel move from theory into practice. For now, we explore. Every black hole we study, every particle experiment we run, every glimpse we get of the early universities bring us closer to a deeper understanding of time. And with understanding comes the possibility of control. Time travel may not be possible today, but the universe has a way of surprising us. When we talk about time travel, one of the greatest obstacles is energy. Warping space-time takes incredible amounts of it. And the more we warp it, the more energy we need. To build a warp bubble or stabilize a wormhole, we would need not just massive energy, but negative energy. Negative energy is unusual. It can repel gravity instead of attract. We see tiny amounts of it in the Casimir effect, but we cannot produce it at large scales. One idea is to harness the energy of black holes. Black holes store unimaginable amounts of energy in their gravity, spin, and radiation. If we could tap into that energy, it might be enough for time travel. But black holes are dangerous and difficult to control. Another possibility is the quantum vacuum. Even empty space is filled with fluctuating energy. If we could harness this vacuum energy, we would have a nearly limitless source of power. But we don't know how. Some propose building machines on a cosmic scale. A Dyson sphere, for instance, could capture all the energy output of a star. That would be enough power to manipulate space-time. But building a Dyson sphere would be an engineering challenge beyond anything humanity has attempted. We might need to dismantle entire planets just to gather enough material. Energy is not the only challenge. We need precision control. Warping space-time is dangerous. A small error could have catastrophic consequences. This is why physicists like Michio Kaku talk about type I civilizations on the Cartesian EV scale. Tie a civilization that uses all the energy on its home planet. I1 that harnesses all the energy of its star. I1 that controls energy across an entire galaxy. Humanity is currently at type 0.7. Time travel may require type I or even type II status. This raises an interesting question. If advanced civilizations already exist, could they have mastered time travel? And would we even recognize the evidence? For now, humanity must work with the tools we have. We are only beginning to generate clean energy on a planetary scale. But technologies like nuclear fusion and quantum computing could bring us closer. And once we have the energy and precision we need, time travel might move from fantasy to reality. Next, we must consider something just as important as physics and energy: the paradoxes and dangers that come with time travel. Because even if we can build a time machine, we must be ready for the consequences. Even if we could build a time machine, we would still face one of the biggest challenges of all: paradoxes. Paradoxes are logical contradictions, scenarios where cause and effect break down. And time travel is full of them. The most famous is the grandfather paradox. If you travel into the past and prevent your grandparents from meeting, you erase your own existence. But if you were never born, how could you have traveled back in the first place? This paradox shows that backward time travel could destroy causality, the fundamental order of events that makes reality make sense. There are other paradoxes too. Consider the bootstrap paradox. Imagine a time traveler who goes back and gives Shakespeare a copy of Hamlet. Shakespeare publishes it as own. Centuries later, the same time traveler reads Hamlet, goes back, and gives the same manuscript to Shakespeare. Where did the play come from? It exists, but it was never created. This is a causal loop, an object or idea with no point of origin. Then, there's the predestination paradox. But by trying to change the past, you end up causing the very events you were trying to prevent. In this case, your actions are not only consistent with history, they are required for history to unfold. This type of paradox raises troubling questions about free will. Do we have control over our choices, or are we just fulfilling events that have already been determined? To resolve these paradoxes, physicists have proposed several ideas. One is the Novikov self-consistency principle. It suggests that the universe prevents paradoxes by making all events self-consistent. If you travel to the past, you can interact with it, but you cannot change it in a way that creates contradictions. Every action you take was always part of history. Another idea is the many-worlds interpretation. In this view, if you travel into the past and change something, you create a new branch of reality. Your original timeline continues unchanged, but you can never return to it. This solves the grandfather paradox. If you prevent your grandparents from meeting, you don't erase yourself. You simply create a universe where you were never born, while your original universe remains intact. The many-worlds interpretation is elegant, but it introduces new questions. Does each new universe have its own copy of all matter and energy? What happens to the traveler? Do they become permanently stranded in the new branch? And how would we ever test this idea? Some scientists suggest that paradoxes might not be a problem at all because backward time travel may simply be impossible. Stephen Hawking's chronology protection conjecture argues that the laws of physics prevent time machines from functioning. Any attempt to build one would fail, or the time machine would be destroyed before it could be used. This would ensure paradoxes never arise. But the truth is, we don't know. Until we understand the nature of time itself, we cannot be sure whether paradoxes are unavoidable or whether they simply point to gaps in our knowledge. Paradoxes also have profound philosophical implications. If time travel is possible, what does that mean for free will? Are our choices truly our own, or are we simply following a script the universe has already written? If we could see the future, would we be able to change it? Or would any attempt to change it just ensure the future unfolds exactly as predicted? These questions aren't just abstract. If time travel allows us to alter the past, we must be ready for the consequences. A single change could ripple forward in unpredictable ways. We could erase entire civilizations without realizing it. Or we could trap ourselves in causal loops, repeating the same events forever. This is why many scientists believe that time travel, if it is ever possible, must be approached with extreme caution. The ability to rewrite history is a power unlike any other. Used wisely, it could save countless lives. Used carelessly, it could destroy everything we know. In the next section, we will look at the technological challenges of building a time machine, because even if the physics allows it, the practical obstacles are staggering. If we want to build a time machine, we must face reality. The technological challenges are enormous. Even if the laws of physics allow time travel, building the machinery to make it happen may be one of the hardest things humanity has ever attempted. The first and biggest obstacle is energy. Warping spacetime requires unimaginable amounts of it. To bend spacetime enough for a small bubble of time travel, we might need more energy than exists in entire stars. And that's just to create the effect. To sustain it long enough for a person or a spacecraft to travel safely would require even more. But energy is not the only issue. We also need to solve the problem of precision control. Manipulating spacetime is dangerous. A tiny error could tear apart the time machine, the traveler, or even entire planets. Consider the challenges of building a wormhole. We would need to find or create one, stabilize it with exotic matter, and position its mouths exactly where we want them across both space and time. If the wormhole shifts even slightly out of alignment, you could emerge light-years from your intended destination, or worse, inside a star or solid rock. Then there is the issue of shielding. Traveling through warped spacetime could expose the traveler to extreme radiation. A time machine would need protection far beyond what we use today for spacecraft or particle accelerators. It would also need to shield the traveler from gravitational forces strong enough to crush them. We would also need to solve the navigation problem. Time travel It's not just about moving through time, it's about moving through space and time together. The Earth is constantly moving. It spins on its axis, orbits the Sun, and moves with the Sun as it orbits the galaxy. If you jump 100 years into the future or the past, Earth will no longer be in the same place. Without precise navigation, you could end up in the vacuum of space, far from any planet. One solution would be to anchor the time machine to Earth's position in space-time, so that you always arrive where the planet is. But that requires calculations so complex, we may not yet be capable of them. We would need to track the motion of every object in the solar system, galaxy, and possibly the universe, across vast stretches of time. Then there is the issue of scale. If we ever build a time machine, will it be a small device, like in the movies, or something massive, like a space station? We don't know. But based on the energy requirements, the first time machines are likely to be enormous, perhaps the size of a planet, or larger. This raises questions about control. Who operates such a machine? Would governments or corporations decide when and where to travel? Would ordinary people ever have access to it? The ethical challenges are as great as the technical ones. The ability to change the past or to see the future would be the ultimate form of power. If one group controlled time travel, they could rewrite history in their favor. They could erase rivals, manipulate economies, and maintain dominance forever. Even if time travel were restricted to science, accidents could be catastrophic. What if a single mistake erased the world we know? What if we returned to find that history had been rewritten beyond recognition? And then there is the psychological impact on travelers themselves. Imagine witnessing the past or the future firsthand. Imagine seeing how your actions might alter everything. Could you resist the temptation to change events? Would you ever be the same? These are problems we cannot solve with technology alone. They require wisdom, restraint, and global cooperation. But humanity has a poor track record of using powerful technologies responsibly. We still struggle with nuclear weapons, climate change, and artificial intelligence. Time travel would be an even greater test. Some scientists argue that because of these risks, time travel should never be attempted. The dangers to humanity and to reality itself are simply too great. But others believe the potential benefits are worth the risk. We could learn from the past. We could prevent disasters. We could ensure humanity as survival in ways we cannot yet imagine. Ultimately, the decision may not be ours to make. If time travel is possible, future civilizations, or even alien civilizations, may already be using it. We may be living in a timeline shaped by travelers from the future, without even realizing it. In the next section, we will explore the possibility that time travelers might already be among us. If time travel is possible, we have to ask a profound question: are we already being visited by time travelers? It's a question that blends science, philosophy, and science fiction. But it's worth asking, because if advanced civilizations, human or alien, can manipulate time, they might already be shaping our reality. The idea may sound far-fetched, but consider this: the universe is 13.8 billion years old. Life on Earth has only existed for a tiny fraction of that time. If intelligent life evolved elsewhere millions or billions of years before us, some civilizations could be vastly older and more advanced. Physicist Michio Kaku has suggested that alien civilizations could be millions of years ahead of us. If humanity can one day achieve time travel, then civilizations far older than ours may already have done so. And if that's the case, they might travel not only across space, but also through time. This brings us to the Fermi paradox. If intelligent life is common in the universe, why don't we see it? Perhaps the answer is simple: advanced civilizations don't travel the way we imagine. They don't build fleets of slower than light starships. They travel through space-time itself, moving instantly to any point in space and time. If so, they could visit any planet at any moment in history, including Earth. But if time travelers are visiting us, why don't we see them? One possibility is that they are careful not to interfere with our timeline. If they are observing us, they may be following strict rules to avoid detection and prevent paradoxes. Another possibility is that their technology is so advanced we cannot recognize it. They might blend seamlessly into nature, appearing as nothing more than cosmic background noise. Some researchers even suggest that UFO sightings could be evidence of time travelers. The strange characteristics of these objects: their speed, their ability to change direction instantly, their disregard for inertia don't match any known technology. Could they be machines capable of manipulating space-time? We have no proof, but the idea is intriguing. There's another possibility: time travelers may not be physical beings at all. If a civilization becomes advanced enough, it might upload consciousness into machines or energy-based forms. Such entities could travel through time without needing spacecraft or even biological bodies. They could be observing us right now, invisible to our senses. Time travelers might also have visited Earth in the distant past, long before humans evolved. If so, we might never find evidence. Or perhaps they influenced early human civilizations in ways we don't yet understand. This idea has inspired countless myths and legends, stories of gods descending from the sky, or mysterious monuments like Stonehenge and the pyramids. There's no scientific proof, but it raises interesting questions about our origins. Some scientists even suggest that we ourselves could be the time travelers. If humanity survives for millions of years and masters time travel, we might one day choose to visit our own past. Our distant descendants could be studying us right now, quietly without interfering, and we might never know. But there's a less exciting possibility. Time travel may simply be impossible, at least in the way we imagine. If that's true, no one, alien or human, will ever visit the past. The laws of physics may place an unbreakable barrier between us and history. Still, the idea of alien time travelers forces us to think bigger. It reminds us we are part of a vast universe, full of mysteries we have yet to solve. And it challenges us to imagine what humanity might become if we continue to advance for millions of years. If we master time travel, will we be careful not to interfere? Will we explore quietly, leaving no trace? Or will we shape history in ways future generations can never fully comprehend? In the next section, we will look at the dangers of time travel. Because whether or not time travelers are among us, one thing is clear: if we ever gain this power, it will come with extraordinary risks. If time travel ever becomes real, we must face the sobering truth: it will be dangerous. This isn't just about the risks of building a time machine. It's about the unpredictable and possibly catastrophic consequences time travel could unleash on the universe and on ourselves. One of the biggest dangers is changing the past. Imagine traveling back and preventing a small event. Maybe you save one life. Maybe you break one object. But the chain of cause and effect could ripple forward, changing the world in unimaginable ways. This is the butterfly effect, the idea that a butterfly flapping its wings could eventually cause a hurricane on the other side of the planet. In time travel, the butterfly effect would be magnified. A single action could erase entire civilizations. We also risk creating paradoxes. A paradox could destabilize reality itself. If cause and effect break down, we might be trapped in loops repeating the same events forever, or the universe itself could collapse. We have no idea what would happen. Another danger is time contamination. What if a traveler from the future brings advanced technology to the past? Even a single piece of future tech could revolutionize the world overnight. But it could also destabilize society, spark wars, or disrupt the natural flow of history. What if future medicine saves lives that were supposed to be lost? What if weapons from the future end up in the wrong hands? Then there's the danger of knowledge. If we could see the future, how would that affect our choices? Would people stop trying to improve the world if they believed the future was fixed? Or would they panic if they saw a disaster coming? Too much knowledge about the future could paralyze societies or tear them apart. Time travel could also threaten our very existence. If we change the past, we might erase ourselves. Or we could trigger chain reactions that destroy entire timelines. What happens to everyone who lived in the original timeline? Do they vanish? Or do they become trapped in some kind of cosmic limbo? Even careful travelers could cause unintended interference. Just being present in the past could change events. A single conversation, a single glance, might influence someone in a way that alters history. And once the change occurs, it might be impossible to undo. Some scientists argue that we would need strict rules for time travel. We would need to decide who can travel, when, and what they are allowed to do. We might even forbid backward time travel entirely, because the risks are so great. But could we enforce such rules? What if a rogue traveler ignored them? Or if powerful nations competed for control, triggering a new kind of arms race? The ethical challenges are as daunting as the practical ones. Who would decide what parts of history can be changed? Who decides which tragedies must be prevented and which must be left alone? And how do we balance the good we might do against the harm we might cause? Some might argue we could use time travel to fix the mistakes of the past. We could prevent wars, stop pandemics, save billions of lives. But history is complicated. What seems like a mistake from one perspective might be necessary from another. If we prevent one war, might we cause an even worse one? If we save one person, might we doom thousands? Time travel also raises deep questions about morality and free will. If we can change the past, are we writing lives without consent? If we can see the future, do we still have the freedom to choose differently? Or are we locked into a path we cannot escape? Because of these dangers, some scientists believe that backward time travel should never be attempted. The risks are simply too great. They argue we should limit ourselves to forward travel, which already happens naturally through relativity. But others believe the potential benefits are worth the risk. Time travel could help us understand our origins, preserve our species, and explore the greatest mysteries of the cosmos. Time travel is filled with dangers and paradoxes, but it also holds extraordinary potential benefits that could transform humanity forever. The most obvious advantage is the ability to learn from the past. Imagine being able to observe history exactly as it happened, without relying on incomplete records or biased accounts. We could watch the construction of the pyramids, meet the philosophers of ancient Greece, or witness the first humans walking out of Africa. Historians could finally settle debates that have raged for centuries. We could understand our ancestors in ways that books and archaeology could never allow. But the benefits go far beyond curiosity. We could use time travel to prevent disasters. What if we could stop pandemics before they spread? What if we could prevent wars, genocides, or environmental catastrophes? A single intervention at the right time could save billions of lives. We could also use time travel to preserve life. By visiting endangered ecosystems in the past, we could gather DNA samples and restore species that are now extinct. We could preserve cultures, languages, and knowledge that might otherwise be lost forever. Humanity could become the ultimate archivist of Earth's history. Then there's the possibility of learning from the future. If we could travel forward, we might gain access to advanced technologies that could solve today's problems. We could bring back cures for diseases, solutions for climate change, or new forms of clean energy. We could see the mistakes future generations made and avoid them ourselves. Time travel could even allow us to spread humanity across time as well as space. If our species faces extinction, we could relocate entire populations to safer eras. We could establish colonies in the distant past or far future, ensuring that humanity survives even if Earth becomes uninhabitable. This could make us effectively immortal as a species. The benefits are not just practical, they are also philosophical. Time travel could help us answer some of the biggest questions we've ever asked. Where did we come from? What is the true nature of time and reality? Are we alone in the universe? By observing the origins of the cosmos, we might discover how it began and whether there are other universes beyond our own. Time travel might also give us a way to communicate with future generations. Instead of leaving behind books and monuments, we could pass knowledge directly to those who come after us. We could help them avoid our mistakes and build a better world. And they could do the same for us. But these benefits come with a price. Even a well-intentioned trip into the past could have unintended consequences. And bringing knowledge or technology back from the future could destabilize societies in the present. This is why we would need strict rules for how time travel is used, rules that put the greater good above individual desires. One possibility is to create an independent organization dedicated solely to managing time travel. This organization would need to be trusted by all nations and cultures. It would need to enforce clear guidelines and prevent abuse. And it would need to make difficult decisions about which interventions are allowed and which are forbidden. But even with strict oversight, mistakes would be inevitable. History is complex. We might try to prevent one tragedy, only to cause another. We might save lives in the short term, but harm humanity in the long term. This is why some people argue that the best use of time travel might be to observe only, without interfering. By studying the past and future, we could still gain enormous benefits without risking paradoxes or major disruptions. Yet, even observation has risks. What if simply being present in the past changes events? What if the knowledge we gain from the future tempts us to act recklessly? The line between observation and interference could be hard to maintain. Despite these challenges, the potential benefits of time travel are impossible to ignore. It could help us build a safer, more prosperous, and more enlightened civilization. It could allow us to protect not only ourselves, but also the countless other species that share this planet. And it could open up the universe in ways we can scarcely imagine. In the next section, we will ask a final question: when might humanity actually achieve time travel? Because as incredible as the benefits may be, we must be realistic about how far we still have to go. Now we come to the question that everyone wants answered: when will humanity actually achieve time travel? The truth is, we don't know, but we can make some educated guesses based on what we know about physics, technology, and human progress. The first thing to understand is that we are nowhere close. Time travel requires levels of energy and control over space-time that are far beyond anything humanity can currently achieve. We are only just beginning to experiment with tiny effects like time dilation in satellites and particle accelerators. Those experiments prove that time travel into the future is possible in principle, but they also show us how much harder it would be to scale those effects up for humans. To build a true time machine, we would likely need breakthroughs in quantum gravity, a theory that unites general relativity and quantum mechanics. Right now, those two pillars of physics do not work together. Relativity describes the very large planets, stars, galaxies. Quantum mechanics describes the very small atoms and subatomic particles. But at the extremes of the universe, inside black holes, or at the moment of the Big Bang, both theories are needed, and they give contradictory answers. Until we solve that contradiction, we will not fully understand space-time. And without that understanding, we cannot hope to control it. Some scientists believe that a complete theory of quantum gravity might be discovered in the next century. Others think it could take far longer. But even if we find the theory, building technology to manipulate space-time will be another massive challenge. We can make a rough estimate by looking at how humanity's energy usage is measured on the Cartesian scale. As we discussed earlier, I civilization can use all the energy available on its home planet. I civilization can harness the energy of its star. II civilization can control the energy of its entire galaxy. Right now, humanity is at about type 0.7. We cannot yet fully use the energy available on Earth, much less a star. To build a time machine, we might need to reach at least type I status. That could take centuries or even millennia. We would need to master fusion energy, build megastructures like Dyson spheres, and develop technologies that can control gravity and quantum fields. There is also the problem of cooperation. Time travel will not be built by one country or corporation. It will require a level of global collaboration that we have rarely achieved. We would need to share resources, knowledge, and decision-making on an unprecedented scale, and we would need to maintain that cooperation for generations. This is why many scientists think time travel, if it is ever possible, may not happen for thousands of years. But others are more optimistic. Technology is advancing faster than ever before. Quantum computing, artificial intelligence, and nanotechnology are opening doors we once thought were centuries away. It's possible that a breakthrough could accelerate the timeline dramatically. There is also the possibility of discovering natural time machines. If we find a stable wormhole or a cosmic string in the universe, we might be able to use it without having to build one ourselves. But so far, there is no evidence that such structures exist. And then there is a question we cannot ignore. Will we survive long enough to build a time machine? Humanity faces many existential threats, from climate change to nuclear war to artificial intelligence. If we cannot navigate those challenges, we may never reach the level of technology required for time travel. But there is hope. Our species has shown remarkable resilience and ingenuity. We have built civilizations, explored space, and unlocked the secrets of the atom. If we continue to learn and adapt, we may one day unlock the secrets of time itself. It may not happen in our lifetimes. It may not happen for many generations. But the dream of time travel is not just about technology. It is about curiosity, imagination, and the desire to understand our place in the universe. Now we come to the question that everyone wants answered: when will humanity actually achieve time travel? The truth is, we don't know. But we can make some educated guesses based on what we know about physics, technology, and human progress. The first thing to understand is that we are nowhere close. Time travel requires levels of energy and control over space-time that are far beyond anything humanity can currently achieve. We are only just beginning to experiment with tiny effects like time dilation in satellites and particle accelerators. Those experiments prove that time travel into the future is possible in principle, but they also show us how much harder it would be to scale those effects up for humans. To build a true time machine, we would likely need breakthroughs in quantum gravity, a theory that unites general relativity and quantum mechanics. Right now, those two pillars of physics do not work together. Relativity describes the very large planets, stars, galaxies. Quantum mechanics describes the very small atoms and subatomic particles. But at the extremes of the universe inside black holes, or at the moment of the Big Bang, both theories are needed, and they give contradictory answers. Until we solve that contradiction, we will not fully understand space-time. And without that understanding, we cannot hope to control it. Some scientists believe that a complete theory of quantum gravity might be discovered in the next century. Others think it could take far longer. But even if we find the theory, building technology to manipulate space-time will be another massive challenge. We can make a rough estimate by looking at how humanity's energy usage is measured on the Carter-CV scale. As we discussed earlier, pi civilization can use all the energy available on its home planet. I civilization can harness the energy of its star. I civilization can control the energy of its entire galaxy. Right now, humanity is at about type 0.7. We cannot yet fully use the energy available on Earth, much less a star. To build a time machine, we might need to reach at least type II status. That could take centuries or even millennia. We would need to master fusion energy, build megastructures like Dyson spheres, and develop technologies that can control gravity and quantum fields. There is also the problem of cooperation. Time travel will not be built by one country or corporation. It will require a level of global collaboration that we have rarely achieved. We would need to share resources, knowledge, and decision-making on an unprecedented scale. And we would need to maintain that cooperation for generations. This is why any scientists think time travel, if it is ever possible, may not happen for thousands of years. But others are more optimistic. Technology is advancing faster than ever before. Quantum computing, artificial intelligence, and nanotechnology are opening doors we once thought were centuries away. It's possible that a breakthrough could accelerate the timeline dramatically. There is also the possibility of discovering natural time machines. If we find a stable wormhole or a cosmic string in the universe, we might be able to use it without having to build one ourselves. But so far, there is no evidence that such structures exist. And then there is a question we cannot ignore. Will we survive long enough to build a time machine? Humanity faces many existential threats, from climate change to nuclear war to artificial intelligence. If we cannot navigate those challenges, we may never reach the level of technology required for time travel. But there is hope. Our species has shown remarkable resilience and ingenuity. We have built civilizations, explored space, and unlocked the secrets of the atom. If we continue to learn and adapt, we may one day unlock the secrets of time itself. It may not happen in our lifetimes. It may not happen for many generations. But the dream of time travel is not just about technology. It is about curiosity, imagination, and the desire to understand our place in the universe. Time travel has captured our imagination. For as long as we've been aware of time itself, we have told stories about it for centuries. We have dreamed of seeing the past and the future, of correcting mistakes and exploring worlds beyond our own. Science has shown us that time is not absolute. It bends and stretches with motion and gravity. We can already move forward in time, even if only by fractions of a second. And we know that the universe may contain paths, wormholes, cosmic strings, quantum effects that could one day allow us to travel farther than we ever thought possible. But we are not there yet. The challenges are immense. We need more energy, more understanding, and more cooperation than humanity has ever achieved. We need to solve paradoxes, avoid dangers, and make ethical choices that will shape not just our world, but the entire timeline of reality. So when will we achieve time travel? The honest answer is we don't know. It may take centuries. It may never happen at all. But the pursuit itself is worth it. Because time travel is not just about reaching the past or the future. It is about expanding what we believe is possible. It is about learning more about the universe and about ourselves. And maybe, just maybe, one day far in the future, a human will step into a machine and vanish only to reappear in another time. When that day comes, it will be the culmination of everything we have ever dreamed of. And it will change humanity forever.